This video is going to give an overview of matching, and it's mostly going to be in the context of case controls, but it's also going to touch on matching in cohort studies and randomized control trials. So when we match, it's typically to control for a confounder. So just a quick review, a confounder is something that's related to both the exposure of interest and the outcome of interest. And when we don't control for it, it can distort the observed relationship between the exposure and the outcome in ways that aren't always predictable. So just an example, if we want to figure out if people who have a fatty diet are more likely to have liver disease, alcohol consumption is something that might influence this relationship, because alcohol consumption influences liver disease, like cirrhosis of the liver and stuff. And also people who consume alcohol regularly might be more likely to regularly go to McDonald's or order pizza at like 3 in the morning, that kind of thing. So the purpose of matching, basically, let's just say we have our cases, this liver disease positive group, and our controls, the liver disease negative group. And among our cases, we have people who are colored black, who have low alcohol consumption, and people who are colored blue, who have high alcohol consumption. Basically, for each case, so this first case is someone with low alcohol consumption, we got to find a control that is their pair, and that is a control that has low alcohol consumption. Same with this case that has high alcohol consumption, we find them a control, like someone without liver disease, who has their alcohol consumption status, basically, so high alcohol consumption. And we do that for everyone. And that's individual frequency matching. So now the example changed to sex. Basically, this is a female case matched to a female control, male case matched to a male control. And basically, it doesn't need to be just one factor. Here we have two binary confounders, sex and age. We've dichotomized age into under 40 or over 40. So the four combinations of our confounding variables are females under 40, males under 40, females equal or greater to 40, and males equal or greater to 40. So our first case here is a female under 40, so we find them a control that's a female under 40. Our next case is a male over 40 or greater or equal to 40, and we need to find them a control that meets that criteria as well, that's in this strata of the, two confounders. And we do that for everyone, and that basically controls for those two confounders in a way that their distribution among the cases and controls is equal. We haven't permitted these confounders to vary in the two groups, and in that way we've kind of isolated the relationship between the exposure and the outcome. So when you're individually matching, you need to do a matched analysis. When you're matching in general, like something I'm going to get to in a second, is by matching, you're basically introducing a kind of selection bias, and that necessitates controlling for that matched factor. But the way in which you control it depends on whether you matched individually or you did frequency matching. So all we've talked about so far is individual matching. And when you do that, you need to do a matched analysis. The bivariate version of that, like a 2x2, is a matched 2x2. And the multivariate version of that is conditional logistic regression. In both of these settings, you're kind of implicitly controlling for the matched factor rather than the more, the type of analytical control you might be more familiar with, where you just include it in the model. That's not what's happening in either of these situations. It's more just like the fundamentals of the analysis takes the matching into account rather than simply controlling for it in the model. And that'll become clear in a second. So so when you when you match individually, you need to do a conditional logistic regression or a match 2x2. So this is what a match 2x2 looks like, and just for comparison, you are probably more used to the regular 2x2, where either it's just disease positive and disease negative, exposure positive and exposure negative, or case and control. With the match 2x2, both instead of it being like this one being about disease and this one being about exposure, they're both about exposure, but this is about controls and this is about cases. So each number here, like for example, each of these 6 in the exposure positive and exposure negative, for exposure positive control, exposure negative case, these are 6 pairs, so it's 12 people. And basically, each of these is describing a pair. So when it's exposure positive and exposure positive, this means that both the case and their matched control have the exposure. And exposure negative means each case and their matched control is exposure negative. Or, yeah, exactly, exposure negative. And these are the concordant pairs. Those are the ones that agree. And it's these discordant pairs that are more useful. I just want to make it clear. I should have just looked it up, but 20 plus 18 plus 6 plus 30. Yeah, so there's 74 values, but these are all pairs, so that means that there's 148 people in the study. I just wanted to make that a little clearer. Okay, so basically it's these discordant cells that are useful, the times in which the case and control have a different exposure value. And the odds ratio is also different, basically, in a matched analysis. It's basically just it's a ratio of two numbers rather than it being like this over this over this over this, which we're typically used to seeing. It's basically just the discordant. It's a ratio of the discordant cells, and the one that goes on top is the time when the case is exposure positive, basically. So this discordant cell is the time when the case is positive and the control is negative, so 18. And this cell is when the case is exposure negative and the control is exposure positive, so 6. So taking the ratio of that, it comes out to 3. And basically, these are the cells that are contributing information. I guess you'd have to ask a statistician for the underpinning, the theoretical underpinning of this, but basically, I think the times when the case and control agree are less informative than the times that they disagree. And basically, the way in which they disagree shows that when they disagree, it's more likely that the case is the one who is exposed and the control is the one who's not exposed. So this gives us an indication that cases are more likely to be exposed here. And yeah, basically, if you have, this is a situation where you don't have confounders, you're just interested in an exposure and an outcome. But as soon as you have covariates you want to also control for, you should be doing conditional logistic regression, because that lets you account for the match data. Basically, you're not including, if we matched on sex, you're not including sex in the model, but you will be, if you're using SAS or something, when you set up your code for the regression, you're going to be telling SAS what you're conditioning on. You're telling SAS you're conditioning on sex, and in that way you're still controlling for sex, but not in the conventional way where you're including it in the model. So yeah, individually matched factors, you're either doing a 2x2 like this, or you're doing conditional logistic regression. Frequency matching is a bit of a different thing. So let's just say we're frequency matching on age. Individuals of certain ages aren't being matched to other individuals. It's more that you're choosing controls so the distribution is the same among the strata of age. That's going to be easier to understand with a visual here. So again, we're matching on age and sex, and here we have the percentage of people who fall into these 4 strata. So we have 4 strata. Again, we have males under 40, females under 40, males over 40, and females over 40. Those are the 4 combinations of our 2 confounders. And basically these blue bars are the percentage of cases that are in each of the 4 strata, basically. So 25% of cases fall into this strata. And what we do is, instead of finding individual pairs for everyone, we basically select controls in a way that the percentage of controls is the same. So 25% of cases are in the male under 40 category, or sorry, 15% of cases are in the male under 40 category, so 15% of controls need to also be in that category. And this doesn't necessarily correspond to the same number of people. If we have 2 controls per case, notice that now the y-axis here went from percentage to an absolute number of people. Basically, the percentage of controls in each category is the same as the percentage of cases, but we have 2 controls per case, so the number of people is number of controls in each category is double, but the percentage, the ratio of controls in each category is the same as cases in each category. So when you frequency match a factor, you need to control for it. You include it in the logistic regression. You usually do like a regular regression, and you would just include it as a covariate. And I guess the bivariate version, instead of doing a matched odds ratio, you'd do like a Mantel-Hansel adjustment. Caliper matching is the next thing I'm going to talk about, and that's where like age is a really common one, where it might not be feasible to find an exact age match for everyone, but like a caliper is like something you use to like measure the size of something that's like a width, basically. Like it's like a, I don't know, it's kind of like a wrench where you like are like rotating this like knob that makes the two ends come closer and closer together, and it lets you take like the width of something in the field. But yeah, it's not important. But caliper matching is a way to match someone. Like, let's just say we're matching on age, and it's like we want our control to be plus or minus 5 years of age. So like if we have this case, and like this is how it's going up, it's like 20, 22.5, 25, 27.5, 30. So this person is 25, and basically they're to be eligible to be a control for them, you need to be like within this caliper of plus or minus 5 years. So these people would be eligible to be matched as a control, but this person wouldn't, basically. Overmatching is matching in ways that harms efficiency or validity. So some examples of that are matching on something that isn't related to the, or sorry, matching on something that's only related to the exposure. So that's something that's not a true confounder. It's just something that's only related to the exposure. And I'm gonna get to it in a second, but basically when you do that, you're making the exposure distribution in the cases and controls more similar than they would have been, and you're basically introducing bias without any gain. Matching on an intermediate or a mediator is also a problem. You shouldn't control for mediators. I have a whole video on mediation analysis that talks about when you should and basically what happens when you do. But yeah, you shouldn't control on something that's on the path between the exposure to the outcome. Okay, so matching on data quality is an interesting one that's kind of like up for debate. People have different opinions on this. So like if your cases are dead and you need to get information from them, you basically usually do a proxy and you talk to their relative and get information from a loved one on that person who's dead. This is more likely to have information bias. It's more likely to be incorrect information than if you're asked the participant themselves. And if controls are asked directly and family members are asked for cases, that's basically differential information bias in the sense that like the rate of error is higher in cases than controls. A way to get around that is, even though controls are alive, if you ask a family member from the control group, or if you ask a family member of the controls about basically like you're asking family members of cases because they're dead, and if you also ask family members of controls, even though the controls are alive, you're imposing the same error on both groups. And that makes sense to me as a naive epidemiologist, and I still subscribe to that opinion, but there's like more advanced epidemiologists who basically take the more like pragmatic view that like, why would you willingly get inferior data? Like if you have the option of getting better data for the control group, why don't you just get better data? And I'm not smart enough to understand why that's okay, basically. So some of the advantages of matching are that it's like a really intuitive control of confounding that a lot of people understand who aren't epidemiologists. It just they get why matching helps. As soon as they have an understanding of confounding, they understand why matching is good. And you can control for things that are difficult to measure, where like for example, certain genetic things, like if you use twins, there's a whole genome worth of genetics that you're controlling for, basically. And you can match on like an index date, like if you're trying to like if you maybe have some like concern about how like biospecimens are holding up over time. You might be able to find both cases and controls that had their like exposure biospecimen taken on the same date, and it's been stored for the same amount of time. Like you can match on time, and that ends up being useful in different situations. There's way more disadvantages to matching than there are advantages, basically. So it's difficult to match on multiple factors. Like I showed you age and sex, but as soon as you're matching on like 3 or 4 factors, there's so many combinations that you might have a case where you're unable to find a control that is a match for everything. And you may end up having to throw away that case because you don't have a control for them, and that is a big problem because cases are typically way more valuable. You can't estimate the effect or any interactions with the matched factor because it's not included in the model in a conditional logistic regression. But when you do frequency matching and you are including in the model, just because it's in the model doesn't mean you can interpret its coefficient. It doesn't really mean anything because you're not looking at its distribution on its own. You're looking at the distribution you created, and that sounds kind of weird, but basically like you're including it in the model, but it means nothing. It can result in overmatching, which we talked about. It can decrease precision when the match factor isn't a confounder. Like I was just saying, it can be that's kind of related to overmatching. It can have external validity issues where you have this population that's matched and the world isn't matched, so it's different in that way. It can diminish the association if it's really related to the exposure, and that's something I'm going to get to in a second, where like if they're basically the more related to the exposure the matched factor is, the more similar it is to essentially just matching on the exposure, and that defeats the purpose because we're trying to see how exposure differs in cases and controls. And when you match on something that's related to the exposure, you're kind of matching on the exposure almost. And you end up like screening way more controls than you need. So like let's just say there's a really common combination of your confounders, and you reach your 4-to-1 ratio of controls to cases. From then on, whenever you screen someone who has that combination of confounders, you're gonna have to discard them even though you put effort into screening them, because we've already reached the maximum number of people to assign to those cases. So yeah, matching kind of introduces selection bias, and that's an interesting idea that I just learned about like just now reading the textbook, which is it's pretty neat. So like I was saying at the beginning, a confounder is related to both the exposure and the outcome. And selection bias is when like the distribution of the exposure and outcome differs in your population than the source population. And when that happens, it's basically because your criteria for inclusion into the study is somehow related to both the exposure and the outcome. So in the very basis of a case control study, you're selecting based on the outcome. So that's a given because we're choosing how many people are outcome positive and negative in our study. But when you match on a confounder, that's something that's also kind of related to the exposure. So now, by design, you're including in the study, it's related to the outcome, but now it's also kind of related to the exposure, and you're introducing selection bias, and basically it's basically superimposing selection bias over confounding, because selection bias is slightly easier to control and just a little more, I don't know if that's the right way to say it, it's more like selection bias, and it's trading selection bias for confounding bias, more like it, and selection bias, like by doing this it's more efficient. That'll become clear when I take that to its extreme. That's sometimes helpful to understand something is taking it to its extreme. So yeah, superimpose, yeah. So you're introducing, when you match on a factor that isn't a confounder, you're basically introducing this selection bias, but it's not trading a confounding bias for a selection bias, it's just creating selection bias basically. So if the exposure is perfectly correlated to the matched variable, then you are matching on exposure, and the exposure distribution in your case and control group is identical, and you've eliminated any effect that exists in the real world. Residual confounding is something I just want to talk about briefly. So when you caliper match, there's likely some, like, a little residual differences in age between the two groups. And in that way, if you include the variable in the model, you can control for the confounding that remains. And the coefficient is still meaningless. Like I said before, it's basically just there to, it's not there to learn about how the match factor is related to the outcome. It's there just to control for the bias you've created. So some really common things to match on are like neighborhood, because there's a lot that comes there's a lot that's similar to people who live in the same neighborhood. They might be exposed to the same pollution. They might be of the same similar socioeconomic status and stuff like that. So controlling for neighborhood can control for all of these other things that are harder to measure. Controlling for siblings is great because you can control for a bunch of genetic factors, as well as like you're controlling for like both nature and nurture in a lot of ways. And I already talked about controlling for an index date, and that's, yeah, it's basically like if time is important in some way, like storage of specimens, controlling for that time can basically be done by matching on some index date. Matching in cohort studies is something I'm going to talk about briefly. So, like, it's mostly a thing in case control studies, but it can also be done in cohort studies. So here, everyone is disease negative, but we have these combinations like exposure negative, confounder negative, exposure positive, confounder negative, exposure negative, confounder positive, and positive for both the exposure and confounder. So those are our 4 combinations of exposure and confounder. And we have our exposure positive group and our exposure negative group. So here we have someone who's exposure positive and confounder negative. We're basically matching them to someone in the exposure negative group who also doesn't have the confounder. And this person is in the exposure positive group and has the confounder. We basically find someone in the exposure negative group who has the confounder. And we do that, and now our exposure positive and negative group have the same number of people who are confounder positive and negative. Matching in randomized control trials is basically block randomization within matched pairs. So I did a video on block randomization that might be helpful to look at. So we have these 2 groups that, like, I've shaded in slightly different colors of blue, these matched pairs, where within each matched pair we have people that are the same age. And let's just say we have 2 treatments, and there's treatment A and treatment B, and there's basically 2 ways to organize that combination, A, B, or BA. It gets more complicated when there's like 4, but yeah, there's basically 2, and we randomly assign each pair A, B, or BA, and yeah, within each pair, like someone who's 33 gets sent to treatment A, and someone who's 33 gets sent to treatment B, and so on. And that way the age distribution ends up the same in the 2 treatments.